Hi everybody. This video is a continuation of our discussion in section 4.1, Introduction to Probability. In our previous video, we discussed probability, and we also discussed the three notions of probability, so we don't need to talk about that. So here we will focus on sample spaces, and in a subsequent video we will talk about the law of large numbers. Now, as we mentioned before, the sample space is a collection of all the possible outcomes for an associated experiment, which is pretty straightforward to do if you're talking about rolling a die or flipping a coin. If you're rolling a die, there's there's 6 items in the sample space. You know what they are. If you're tossing a coin, you have two possibilities, typically known as heads or tails. But what if you actually have more complex scenarios? How do you actually figure out what the sample space happens to be? Well, we're going to show you this by example. So let's take a look at this example and see see how we can actually go about solving it. So suppose you wish to paint 3 rooms, and you have the following choices. Room 1 can be either red or green. Room 2 can either be blue, purple, or white. And room 3 can be orange or yellow. Those are some weird combinations, but that's what we have here. And your first choice is, well, how would we list out the sample space? And the way we do this will be in stages using a tree diagram, and you'll notice that the sample spaces are multiplicative in nature. So let's go ahead and get started. Okay, now remember, room 1 can be 2 colors. Those colors are blue or red or green. Okay, so that takes care of room 1. If we looked at room 1 and room 1 alone, there are 2 possibilities. But now that we have room 1 taken care of, let's take a look at room 2. Now first, room 1 can be red. And then room 2 can be blue, purple, or white. So notice here, we actually now have 3 possibilities, 1 times 3. However, room 1 can also could be green, and room 2 can, yes, you guessed it, be black or blue, purple, or white. Now we have a total of 1, 2, 3, 4, 5, 6 possibilities. And notice that we are generating a tree. All right, and now finally, so here, now we had that room 1 can be red, room 2 can be blue, room 3 can either be orange or yellow. So now we have 2 possibilities here. Room 1 can be red, room 2 can be purple, room 3 can also be, once again, orange or yellow. So notice room 3 generates for us a third tier of a tree, and this is actually called a completely populated tree, or a full tree. And if you continue along this thinking, it makes perfect sense that this will have orange and yellow here, here, and here. Okay, so this tree basically maps out our sample space. But what is the sample space? The best way to determine the sample space is to go down each branch of the tree. For example, one possible outcome is going to be room 1 being red, room 2 being blue, and then room 3 being orange. The other possibility is room 1 being red, room 2 being blue, and room 3 being yellow. And if we continue walking down every single path in this tree, we will identify every single member of the subspace. This right here is your sample space. Not subspace, sample space. And notice that we were able to do this by drawing out a tree for every single possible outcome. The next question we have are how many elements are in the sample space? Well, if you count these out, there would be 12. Another way to look at this is as follows. There are 2 possible outcomes for room 1. There are 3 possible outcomes for room 2. There are 2 possible outcomes from room 3. Let me actually go ahead and write that down because that might be a little useful. So once again, we have 2 possible outcomes for room 1. We have 3 possible outcomes for room 2 and 2 possible outcomes from room 3. And look down here. 2 times 3 times 2 is equal to 12. There are 12 elements in your sample space. So if you're asked to determine how many elements in your sample space, you can how many elements in your sample space, you can ask yourself, well, how many outcomes are there in each stage? And then you can multiply those things together. Okay, the next question here is, what is the probability that room 1 is red, room 2 is white, and room 3 is yellow. So what's the probability, using our code here, that we have red, white, and yellow? Well, that's going to be the number of outcomes associated with the, or the number of outcomes associated with red, white, and yellow, all right, divided by the total number of elements in the sample space. We've just determined the total number of elements is 12, and there is exactly one outcome associated with that combination. There it is. Your answer will be 1/12. If you wanted to write it as a decimal, it would be equal to 0.0833. Okay, so let's take a look at another problem. This is a coin toss problem. And here, you're going to toss a coin 10 times, and the side on the side on the top is going to be observed. And the question here is, what is the size of the sample space? Remember, we're tossing the coin 10 times. That's kind of like having 10 stages. So we have 1, 2, 3, 4, all the way to 10, but we probably don't need to go that hard. Okay, so let's suppose you toss the coin once. Okay, there are going to be two possible outcomes: heads or tails. Okay, the size of the sample space for the one coin toss is going to be 2, or 2 to the first. Okay, what if we toss it twice? Well, then the first outcome could be head. The second one can be either heads or tails. Okay, the first outcome can be tails, and the second one could be heads or tails. So we're basically drawing the exact same tree we did before. It's just with the same it's just with heads and tails. So, and notice here we have 1, 2, 3, 4 possibilities, or 4 total outcomes, or 2 squared. Okay, let's go to 3. This can be heads or tails. This can be heads or tails. This can be heads or tails. And same thing over here. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 possible outcomes, which ironically happens to be equal to 2 to the third. So if you toss the coin 4 times, how many possible outcomes will there be? Well, I'm hoping that you can deduce, or maybe I should say induce, since we are using induction here, that there would be 2 to the 4th possible outcomes. 2 to the 4th happens to be equal to 16. 5 times, okay, I know I'm killing a dead horse here. Yeah, 2 to the 5th, which would be 32 times. Okay, so now I think we can go ahead and try to induce or deduce what would happen if we tossed the coin 10 times. If we toss the coin 5 times, there's 32 possible outcomes, 2 to the 5th. If we toss the coin 10 times, there will be 2 to the 10th possible outcomes, and that would be 1024. And that is how you can actually deduce this. Now, the next part is, what is the probability of getting all heads? So you toss the coin 10 times, and you get 10 heads. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, the probability of getting all heads, I'm just going to say H for here, is going to be equal to the number of outcomes associated with all heads divided by the total number of outcomes. Okay, remember the total number of outcomes we just finished deducing is 1024. How many ways can you get all heads? Only one way. First one's going to be, it's basically just going down this tree, right? It's going down this tree right here. There's only one way to get all heads. And that would be your answer, 1 over 1024. If you wanted to write that as a decimal, it would be very uninteresting. It would be 0.00010, which is not a very interesting number. That's what it would be. Okay. Now, what is the probability of getting at least one tail? There's a couple of ways of doing this. The first thing is that the first thing that you could do is basically count all the outcomes that have at least one tail. but it might be, which would be a daunting task. But another thing you can do is just take a look at our previous example. This is, which is all heads. Okay? This is the event associated with having absolutely no tails. Okay? And this is only, every other event every other event will actually have at least one tail. Okay? So if that's the case, then the number of outcomes associated with, I'm just going to call this 1t, at least one tail, is going to be every single outcome with the exception of this one, which would give us 1023. And if that's the case, then the probability of getting at least one tail is going to be equal to the number of outcomes, which has at least one tail, divided by the total number of outcomes, which is going to be equal to 1023 divided by 1024. 24. One other thing I wanted to mention here is this. The probability of getting all heads plus the probability of getting at least one tail is equal to 1 over 1024 plus 1023 divided by 1024. More importantly, the probability of getting at least one tail is equal to 1 minus the probability of getting all heads. And that is because the event of having at least one tail and the event of having all heads are actually complements of each other. And this is an illustration of the complement rule. Okay, so this brings me to my very last part here. I don't want to do this here. I want to do this over here. Okay, suppose a coin is only tossed 3 times. Write out the sample space for the given experiment. We've done this before. We're going to use H to indicate heads and T to indicate tails. Okay, so one toss. Okay, there's 2 possible outcomes. Heads, tails. Let's toss it a second time. We have 2 possible outcomes. We can have a heads here, a tails here. Heads, tails. Toss the coin one more time, or toss the coin one more time. And once again, we have those 2 outcomes. Heads and tails. Heads and tails. Heads and tails. Heads and tails. Okay, now, how can we actually write out the sample space? The same way we did before. Just walk on down the tree. I don't need to change color. So here we have heads, heads, heads. Here we have heads, heads, tails. Here we have heads, tails, heads. H, T, H. Heads, tails, tails. H, T, T. Here we have tails, heads, heads. T, H, H. Tails, heads, tails. T, H, T, tails, tails, heads, T, T, H, and then all tails. And that is our sample space. And that is all that I have for this particular video. Please stay tuned for a follow-on when we will go over a couple of more examples. And until then, this is Bob Boyle, signing off.